If Module 1 was about the rules of the road in electrical design, Module 2 is about driving with skill and efficiency, applying those rules to real-world projects, ensuring protection systems are integrated, and adapting designs to modern energy sources. This module has 3 major goals. Equip you with the ability to design and verify both single and polyphase installations to high professional standards. Deepen your understanding of protective systems, not just what they are, but why they are chosen and how they are installed. Explore how alternative energy sources and environmental technologies fit into electrical design. 1. Advanced design procedures for electrical installations. 1.1 Load calculations in detail. Designing electrical installations begins with accurate load calculation. This ensures that cables, switchgear, and protective devices can handle the expected current without overheating or voltage drop beyond acceptable limits. Steps in detailed load calculation. List all loads, appliances, lighting, motors, heating, and specialist equipment. Determine the rated power for each load, converting to amperes using the appropriate supply voltage. Apply diversity factors, realistic estimations that not all loads run at full capacity simultaneously. Sum total demand and add margin for future expansion. Verify supply capacity, ensuring the incoming supply from the utility or generator can handle the calculated demand. Example. A commercial kitchen design may list 12 kilowatts of cooking equipment, 5 kilowatts refrigeration, and 3 kilowatts lighting. After applying diversity, the total design load might be closer to 15 to 16 kilowatts rather than the raw sum of 20 kilowatts. 1.2 Voltage drop calculations. Voltage drop is the reduction in voltage from the supply point to the point of use due to resistance in the conductors. BS 7671 recommends maximum voltage drops. 3% for lighting circuits. 5% for other uses. Design tip: always calculate voltage drop for the longest circuit run in your design to ensure compliance. 1.3 Short circuit current and protective device selection. A protective device must be able to interrupt the maximum possible short circuit current without damage. The prospective fault current is calculated based on the supply impedance and conductor sizes. Circuit breakers, fuses, and residual devices must be rated accordingly. 2. Protective systems in electrical installations. Protective systems are the heart of electrical safety. They guard against overcurrent, electric shock, fire, and equipment damage. 2.1 Protection against overcurrent. Overcurrent protection includes overload protection, to prevent overheating of conductors and insulation when currents exceed their continuous rating. Short circuit protection, to clear faults rapidly and safely. 2.2 Protection against electric shock. This involves automatic disconnection of supply when a fault occurs. Residual current devices, RCDs, to detect small leakage currents. Proper earthing and bonding to maintain safe touch voltages. 2.3 Surge protection. Transient overvoltages from lightning or switching operations can damage sensitive equipment. Surge protection devices, SPDs, are installed to divert these surges to earth before they reach critical loads. 3. Commissioning process. Once the system is installed, commissioning verifies that the design intent has been met and the system operates safely. Commissioning steps include preliminary checks, verifying installation matches drawings and specifications. Electrical testing, continuity, insulation resistance, polarity, earth fault loop impedance, and RCD testing. Functional test, confirming all equipment operates as intended. Handover documentation, including circuit schedules, as-built drawings, and test certificates. 4. Alternative energy sources in electrical design. The modern electrical designer must integrate renewable and alternative energy systems into installations. 4.1 Solar photovoltaic systems. Design considerations. Orientation and tilt of panels for maximum output. Inverter selection to match array size and load demand. Connection method, grid-tied, off-grid, or hybrid systems. Protection, DC isolators, overcurrent devices, surge protection. 4.2 Wind energy systems. Small-scale wind turbines require adequate wind speed analysis. Correct sighting to avoid turbulence. Power electronics for voltage regulation. 4.3 Battery energy storage. Batteries allow storage of renewable energy for use during peak demand or outages. Designers must consider battery chemistry and lifespan. Charge/discharge control systems. Safety measures for thermal runaway prevention. 5. Environmental technologies in electrical design. The environmental impact of electrical installations is now a design priority. Technologies include LED lighting systems with automated control, energy monitoring and smart metering to optimize usage, electric vehicle charging stations integrated into building supply, heat pumps powered by renewable electricity. 6. Factors affecting choice of alternative energy. Key factors include site conditions, solar exposure, wind availability. Load profile, steady loads benefit more from solar, variable loads may benefit from hybrid systems. Budget and incentives, government grants or feed-in tariffs. Maintenance requirements, some systems demand higher upkeep. Conclusion of Module 2. By the end of this module, you should have a firm grasp of how to calculate, design, and verify both single and polyphase installations. How to integrate protective systems to meet safety and performance requirements. How to incorporate alternative energy and environmental technologies into your designs. Electrical installation design is no longer just about supplying power, it's about doing so efficiently, safely, and sustainably, while anticipating the needs of the future.